share. So yeah, so are there any questions first about the material from yesterday or about the questions in the problem document? So, so let me start. So just to review a bit what I did last time. So I introduced finally the equation of generalized hydrodynamics. It took some time, but I think we had a good context for it, right? We know where it comes from, what it means. So it's the equation of Euler scale hydrodynamics that is obtained by using all the conserved quantities. But in fact, the way that we account for all the conserved quantities is quite special. It's characteristic of integrability and has to do with the scattering structure of integrable system. So this is what I explained yesterday, that scattering is both elastic and factorized in integrable systems, meaning that if you start with a system where you have particles that are very far from each other, particles may be solitons, maybe collective excitations of quantum chains, or maybe the actual particles of the model, like the Liebdeniger model, or like the hard rods. Then you let them kind of collide into each other and do a scattering process. A lot of stuff happens, complicated, there's interaction. When they come out, they have the same momenta. All the momenta are the same. And not only that, but their scattering property, scattering phase, or scattering shift are factorized, as if each particle had interacted with each other just two particles at a time. Now, in the hardware, this is clearly the case because it's extremely unlikely and measure zero that you're going to have three rods colliding simultaneously. They always collide just one after the other or one before the other. In general, though, that's not necessarily the case. When you have solitons interacting in the KdV equation, they can all come towards each other more or less at the same time. The interaction takes a bit of time, solitons are deformed. Nevertheless, after interaction, solitons separate, have the same shape as before, same asymptotic states, have the same velocities as before, and have shifts which are as if each soliton had interacted just with the other two at a time. So two-body scattering shift is the only thing that remains out of the many-body scattering procedure. So this is scattering theory, and then that gives rise to an intuition for how to describe the many-body integrable systems. The intuition then tells us that this is the equation. That equation there is the equation that describes with quite a good accuracy the positions of these quasi-particles as they go along within a gas. So the position of solitons, for instance, even if the KdV field looks very messy when you have a lot of solitons interacting with each other, you don't see the solitons anymore. You don't see these nice bumps. Still, you can say there should be a soliton more or less there, even if I don't see it. And as you go further, larger time, they separate out, and indeed the solitons is there. So this equation encodes the fact that scattering is elastic and factorized. So it tells you that if you go from time minus infinity to time plus infinity, the positions yn will the position xn of the solitons or the quasi-particles, the rods, whatever quantum quasi-collective excitation, the positions will simply be linear trajectories, which is this yn, plus a modification due to the sum of two-body scattering shifts. And that's this other term. So that equation implements this intuition. And then you just have to take that equation and see what happens with a system of that type, with this equation, the dynamics of that type at large scale. Then you do the calculation exactly like in the hard rods, and you find that the effective velocity that describes the current is given by this interesting integral equation, and that the density in phase space is given by that equation. So at the basis of it, of course, is the idea that since all the momenta are conserved, then you have still an infinite number of quantities which can be interpreted as a distribution of momenta. And the proper interpretation, I think I discussed a bit last time, is that you think of So if you have a maximal entropy state determined by infinitely many constants of quantity, you put it in a vacuum and let it expand. So you do essentially the black body radiation for that state. Let it expand. What you're going to see are set of momenta, which is a certain distribution of momenta. And that distribution can be any function. It's not just Gaussian like you have in ideal gas, it can be any function. And what are these functions? Well, these characterize the state. So there's a mapping between the betas and the GGEs and these function distribution of momenta. And these distribution of momenta are this rho of P. Okay, this rho of P, density in terms of momenta, is the distribution of momenta that you would see locally. If you look locally at the maximum entropy state, and then see what is its content in terms of asymptotic particles. So in fact, this is a continuation of kind of this lecture actually, but so in fact, I just want to say before I come to what I want to say in current lecture, this whole procedure that I'm describing seems a bit abstract, was experimentally realizable. So rho of P x t is experimentally observable. Although it looks a little bit abstract the way I describe it, you take a cold atom gas. The experiment I showed pictures about the beginning, first lecture. This is composed of atoms interacting with each other. It's described by the Liebninger model. And what you do when people are attempting now to do that with more and more precision, you have your gas, which is essentially in 1D, a 1D tube, constrained by some external potential. And you extract out of this gas a fluid cell, a little bunch of space there. You extract the atoms from there. They should be, so if this fluid cell is of a length L, which is much smaller than L, curly L variation scale. So the fluid cell length, capital L, much smaller than the variation scale. If it's the case, then that should look homogeneous in space, more or less time independent, homogeneous in time, or stationary in time. And it should look like a maximal entropy state, a GGE. So experimentally, they take that bit, this bit of atom, they put these atoms, so there's a lot of atoms here, there's atoms everywhere, right? They put them in the vacuum and they let them expand. So put in the vacuum and then let them expand. So then the atoms start expanding at different velocities. The faster one go further, the slower one don't go as far, etc. And if you look at very large time, the distribution of momenta that they will have, the pi, the distribution of momenta is this rho p x t. So here you are in a fluid cell at xt, so at a given position after a certain time, right? And that's how you can explicitly measure rho pxt. How do you actually take a bunch of atoms, put them in a vacuum? Well, they don't take that bunch of atoms. Instead, what they do, they shine light on the rest of the atoms and let them go away suddenly. And so then these, except for this little bunch of atoms, so this fluid cell then finds itself in the vacuum suddenly, and then you let them expand, right? So if you want to observe different fluid cells, you have to reproduce the experiment many times. But you can do that. Even when you let them expand, you see the asymptotic momenta is exactly the meaning of this rho p xt, the distribution of asymptotic momenta for a fluid cell at xt. So it's really experimentally observable and should satisfy the GGG equation, which is that equation there. Okay. So this is the meaning of this equation, physical meaning of rho p xt, and the origin of it as a kind of intuitive origin via some effective kinetic equation. And yeah, so that's kind of mainly what I said last time. Any questions about that?
Yeah, so just to say, so this Kinoshita's experiment on this Newton's cradle, was it of this kind that you just described, of finding out rho pxt?
So no, it was not.
I
This
see.
is more recent. It's recent stuff that people now, in recent experiment, maybe last 2, 3 years, people have started to do that. And one of the proponents of this is Jérôme Dubail. He's a theorist and also has been collaborating with experimentalists and kind of forcing them to actually do that and then measure this rho pxt, because it's
I
interesting.
see.
Originally, they were measuring something different and then interpreting via a lot of interpretation arguments something related to rho p, but it was never direct.
I
Mhm.
see.
Yeah,
So who are
exactly.
these people? Guys, say the name again, please.
So
Who are,
the so Jérôme Dubail,
okay, okay. I see, I see, I see.
you probably know him. He's been working a lot on many things, in particular on GHG and in relation to atom gases. I mean, the first experiment that verified the GHG equation. I was part of it, but Jérôme was, and the experimenters were kind of the leader of that.
Okay.
And we were not verifying the full equation. We were
Hmm.
just verifying the consequence of this equation for the density of atoms. So
Right.
the integration over P of rho of P. But now he's pushing to check the full equation and then get this rho of P explicitly.
Okay, thank you.
Other questions?
Benjamin, I mean, is it clear that these equations have as an invariant the GG?
Has what?
The sorry, yeah, the generalized Gibbs ensemble would be an invariant measure for these
Ah,
equations.
yes. Um, so how to say, so in a sense, so anything that's time independent, that's x independent, is invariant. So you put no x dependence invariant, and so any function rho of p. But perhaps what you really want to ask is what is the large time limit of this equation, and is it a GGE? Right. So if rho does not depend on x, then it's invariant. Right. That's it. And if rho doesn't depend on x, doesn't depend on t, then it's just rho of p. And then the question is there for any rho of P an associated GGE? Like it's kind of a separate question, let's say. Um, Given rho of P, which then trivially solve equation, okay, is there a GGE like exponential minus sum over I, beta I, qi? So like, do these beta I exist? Right? And that's a kind of non-trivial, actually, rather non-trivial question, and it's a question about the full relation between these inverse temperatures and the rho of p. So, what is the full space of functions rho of p that we can get that corresponds to the GGEs? And in fact, it is not clear that is always the case. So, not clear, and perhaps not so relevant. Like I put interrogation mark, not so relevant because actually, physically, it's rho of p that you observe more easily than any of these inverse temperatures. So in fact, maybe you started with the idea of Gibbs state, generalized Gibbs ensemble with exponential form, which is natural because it gives rise to decay of correlation. Naturally, when you have exponential of extensive observables, then things decay, correlations decay. But in the end, perhaps one should extend this notion to actually distribution in momentum. So rho of p are the GGs, and kind of that's it. You may ask about what are the betas. Do these betas exist for a certain set of const of quantities? The set that you have, maybe you don't have the full set, but in the end, doesn't matter too much because it's the rho of p that you can actually measure, is the rho of p that are related, simply related to every measurable densities conserved density of any conserved quantities, they are just obtained from this rho of p. You just have to sum over all the particles, the charge carried by the particle times the density of moment of particles with that particular momentum. So I would say forget about the question of GGE now. Rho of p, function of momentum, is what describes your state. Perhaps the more tricky question is there always, so this, given a rho of p, a distribution of momentum, is there always a state which has decaying correlation? That's what we want, right? Decaying correlations are crucial for the whole structure of hydrodynamics. Or are there distribution of momenta which are so bad as singular, such that in fact there's no corresponding state with decaying correlations? This I don't know. So that's the question. What's the space of function rho of p? So the question is space function rho of p that gives rise, that correspond to stationary space-time stationary state which have decaying correlations. That's the crucial question. But I don't think there's any clear answer of that, except in free particle models. Then you can do it. I'm not sure if it has been done, but you can do it. Yeah.
For hard rods, we did some calculations, and in the rho of p, if you have a singular component, then I think you do not have this decaying correlation, and it does not go to.
Indeed, yeah, indeed. Actually, very good point. Yes, I of course I've seen these works, and yeah, okay. So this is there you go. This is an example, right? So when you have a singular component, meaning essentially like you have, for this momentum, many more particles. Maybe you like concentrate on particular particle, their delta function or something like that. Then you destroy this decaying thing. So and then I mean, I don't know, and this can happen maybe dynamically. A lot of the phenomenology can be very complicated. Can happen, right? You do have initial states which, as you evolve in time, suddenly give singular component. You can have that, and then a lot of the stuff of earlier hydrodynamics seemingly break down. The general things that I was talking about, right? About the reverses and all that requires decaying correlation. I don't know. So how do they break down? What changes and all that? Phenomenology gets complicated. So yeah.
So maybe not in the integrable systems, but let's say if we go back to previous lectures, if we are close to phase transition point, then also it can happen, right? Similar things.
Indeed. Actually, this also, I think, connect a bit with a question that was asked, that if you're close to phase, if you're at phase transitions, decay of correlation is not as large, and maybe formally, right, the set of excessive charges maybe is different. So the set of possible functions of p's will be different, or even the notion when you are in a CFT, right, the notion of asymptotic states is not a clearly defined notion. You have different choices of asymptotic particles. So yeah, so indeed there too something like that can happen, and maybe you can have a system where eventually, as you go over time, you get to a temperature which is near to critical temperature. Maybe this is 1D, okay, but and if in higher D, if this happens, then can be problems, right? Or in 1D, maybe you can get to very low temperature. If you start at low temperature, and there are other effects. So there's many effects. Let's say that's the thing. I don't know of a like really super strong general statement than that one can make, like in general. There's a lot of phenomenology that's possible. Other questions? Okay. So one of the things that I wanted to do today then is understanding this effective dynamics, this y equation, this equation. If understanding it from the point of view of quantum models, so Liebniger model. So I started a bit of that in the question problem sheets that I gave. I didn't put a title for this one, but okay. There was a little problem of calculating the time evolution for a free particle wave packet. And wave packet here I understand as a modulation of an oscillatory wave. You can do that, right? So this is the theory of modulation. And here I'm doing it for the Liebniger model, but it's quite general. This is based on that structure. Okay? And the idea is like that. So remember that the wave function has a form. There's a lot of stuff at the beginning which are not so important. I write them, but they don't matter too much. All that stuff doesn't matter too much. Stuff, okay. CS, sum over permutation minus 1 to the permutation order. Times what? And then the thing that mattered was this exponential over phase, I phi, capital Phi of x, where the positions are permuted, and theta. It is capital Phi of x and theta, depends on many x, many thetas. Okay? Has simple form is a x dot theta, like the free particle form, but with a correction, which is 1/4 sum of all the particle different from mn, and then there is a straight phi theta m minus theta n times sine x m minus xn. And that straight phi is the two-body scattering shift, or two-body scattering phase. So e to the I phi theta is the two-body scattering matrix. It's not a matrix, it's just a phase. Because there's no internal particle structure. But if you turn two particles towards each other, something happens, the wave function gets affected by this phase as theta e to the I straight phi. And it turns out if you do calculation, Liebniger model, straight phi is just 2 arctangent theta over c. So this is the explicit function. Okay. Same structure for many models, but for Liebniger model, that's the explicit function. And now, modulation, I want to do something similar to what I was talking about for free particle. So I want to do something like, so you see, here there's a phase. This phase is oscillatory. Okay? So I want to modify this oscillation by some modulation factor. So I think about this kind of oscillatory phase that I modify like that, and then some of the oscillatory phase that I modify like that. And so these are my kind of particles. Okay? Here in that picture, they're all well separated, but they don't need to be well separated. You know? So the way that I modulate is simply by multiplying a function of x. Right? So I can write psi a of x knowing theta as being all these initial constants. I'm going to write them again, but eventually I'll stop writing them. And then instead of just putting the phase, I put function a that depends on all these x's and then the phase, e to the I phi. So there's this function, this modulation function. Or amplitude. Actually, I call that amplitude modulation. And that, now I would like this function to be slowly varying. So really, I'm going to make it on large scale. So I put divided by L. Okay. And now I would like to know how this evolves in time. Okay. And the result, I tell you the result and then derive it. Okay. The result is very interesting under various approximations. Okay. The result is that e to the minus I ht on this psi a, as function of x and theta, is what? Well, has the same form, but with a different amplitude, with AT instead of A, and this different amplitude is so AT of all these x's, right, is A at xt, so some evolved coordinate xt over L, so still at large scale, okay? And xt over L is controlled by a certain equation. I write it explicitly that we choose this function x bar. So this is xt, okay, actually I'll write it like that. X power x of t. Okay. This is a vector, it's many positions, so x n of t over L is some function x bar n of y bar as a vector, okay, evaluated at the original x bar, x vector over L and theta minus theta t comma theta. What are these x bar and y bar? Well, y bar n is exactly our change of coordinate that I showed before. Then as a function now of all these coordinates, all the coordinates and all the theta, it is xn plus 1 over 2L. There's a scaling that I have to put, okay, sum over mn, then curly phi theta m minus theta n, m different from n, times the sine of xn minus xn. Curly phi is just the derivative of the scattering phase, the phase of the scattering matrix, divided by with respect to theta. And that has a form theta square, yes, over theta square plus c square, something like that. I don't remember. No, I should know that, but probably c, 2c. Okay, I don't remember, but something like that. Rational function of theta square. Yeah, I think it's that one. Yes. So
sorry, so this
yeah.
is from the derivative of the tan inverse? Is that?
Yeah, the derivative of the arctan, yeah. So you can do it on Mathematica and tell me what it is.
Yeah, that's correct.
Yeah. So yeah. Okay. So this is, yeah, go ahead.
It's 1 over 2L, this L is there?
1 over 2, you mean here?
2L is there?
Yes, so I have in my original thing, I did not have an L. Now I've put an L. And that's because my modulation has coordinates which are modulated by some large scale. So in this whole computation, there's an L that appears. But to make
in the previous
yeah,
equation, you wrote g bar x bar by L, comma, there was an L.
okay, did I
The previous equation, just
this one?
yeah,
This one. Yes.
yeah.
There's L again because so I should write them with some different notation, but this x is a microscopic coordinate. And the point is that you have to scale it with L to get something finite. So I divide by L. Okay? So if when microscopic coordinate is very large, then it's finite number. And it is that finite number that is modified, that evolves according to this equation. What is this equation? Well, there is this y bar, which is the y's that I had written previously. These are the contracted coordinates in the hard rods. These are the ones that evolve trivially. And what I'm saying is that, yeah, you take these y bars, you put them at x over L. Okay, so when I put x over here, I have a 1 over L. I would have a 1 over L there. Okay, and so if I put okay, I change color. If I put the 1 over L here, kind of divide by L, then I would have divide by L here, right? And then all the L's kind of go away, and then everything is scaled appropriately. So I put y bar at x over L, all these coordinates x over L and theta. And then I evolve it. So the evolution is linear in these y coordinates, like the contracted coordinates of the hard rods, right? And like the more general things, linear. And then what is this x? This x bar is just the inverse, right? So I say y bar n, if I evaluate it at x x bar directly as a vector, comma theta as a vector, I would get x bar of x over L. Sorry. This is the inverse. This x depends on some y bar and theta. I would get, maybe I should not call this y bar, let's say z, okay? Some z, I would get z. Sorry. My notation, I would get zn. Okay, so y bar and x bar, they are inverted of each other. And why I put the bar there, the bar here, is because this is a scale variable. It has to do with this L there. Okay, put a bar because there's an L. When there was previous equation, there was no bar because there was no L. Okay, so it's scale things. Yeah. So yeah. Okay. So y bar and x bar are inverse of each other. For given theta is just fixed, it's kind of just I put theta in there, comma theta, but I could just not put comma theta. Theta is kind of fixed in this derivation up to now. Okay. So what I say that you take your amplitude, you map your scale coordinates, you map the scale coordinates x over L to these y coordinates, which are the freely evolving one. You evolve them with this, and then you map back to scale coordinates x, and this is your time evolution. In other words, time evolution is linear after the mapping to the y, after contraction. So I take away these little, right? That's the idea. And this is a result of applying the Hamiltonian to this modulated wave function, and using simply the Hamiltonian of the Liebniger model and the fact that you know what the eigenfunctions are. Now note that this modulated wave function is not an eigenfunction. If I did not have the A, that is an eigenfunction. Okay? And that I know that diagonalizes the Hamiltonian all of the constant quantity. Okay? But this one is not an eigenfunction. So I need to write it in terms of eigenfunctions to be able to evolve it. Okay? And the idea is writing it in terms of eigenfunction, I evolve it, and I get that result. The result is you shift the amplitude in terms of scale coordinates. You shift the amplitude. So I'm missing some L maybe somewhere, because I want to say AT of x over L. Maybe that was your question. Sorry about that. Apologies. AT of x over L. Yeah. So the amplitude evolve simply by mapping its x's dependence to some y's, evolving them linearly and mapping back to x. Okay? That's the idea. Right? Now, how does that work? So besides the 1 over L and all that stuff, right, that I've put kind of because I know that I have to have a large scale somewhere. Okay? If you want to simplify everything, put L equals 1 everywhere, then perhaps imagine that there's some other scaling that make the x's very small or something like that. But I put the scale, okay. Now, how do I do this? The trick. In the case of free particles, you could do that, and the trick is very simple for free particle, is just to write your amplitude in Fourier transform. So if I go here, if I write this amplitude in Fourier transform, it becomes e to the I qx for the Fourier parameter q, right? And if this was a free particle wave function, this phase then would be e to the I px, and then p plus q is just another momentum, and this is a wave function that diagonalizes the Hamiltonian. So Fourier transform, obviously, is the way to go for free particle. But here is interacting. If I do Fourier transform, is not quite the right thing. But there is a notion that we call the Bethe Fourier transform. And goes like that. You write an amplitude A of x. Now this x is, okay, there are many x's. These are scaled variable. I don't put the L now to be the correct equation still, okay? So this amplitude as a function of its variable, x, say, okay? You write it as an integration over Fourier modes, I call them alpha, okay, of its Bethe Fourier transform. And then you put not e to the I alpha dot x as you would do for usual Fourier transform, but instead I alpha dot y bar of x and theta. So it depends on theta as an external parameter. Theta is not a Fourier parameter, it's just some external fixed parameter. And instead of x is y, and this y bar is that one there. Okay? So there's the L in it, but again, if you want more universal, you put L equals 1. There's an L in it for the scaling. Okay? And there's an inverse, of course. So A beta Fourier alpha is going to be integration dn y over 2 pi n A not transform of x bar of y integrated over comma theta e to the minus I alpha dot y. And then there is the x bar that appear. The x bar is this inverse function, right? It's this x bar there. Okay. So and check that these formally are inverse of each other. The only thing that really mathematically needs to be checked to make sure that this makes sense is that the function from x to y given by that is bijective, is a diffeomorphism. And in the case, if you regularize the sign function a little bit, then it is a diffeomorphism one can show, and so that kind of makes sense if you regularize the sign function a little bit. Okay, but okay, so glossing over this detail, this is the Bethe Fourier transform. And now this is very interesting because if you use that, you can indeed solve the time evolution, and it goes like that. So it's because this total phase of the Bethe ansatz wave function, that one there, okay, that one, has the following property. If you modify a little bit the thetas by plus epsilon, say, plus epsilon, okay, you see that you're going to have some plus epsilon here, and you have to expand this two-body scattering shift phase. And so the result is that phi, if I evaluate it at x and theta plus epsilon for small epsilon, okay, I get phi at x and theta, these are vectors, plus epsilon dot exactly that y function of x and theta. And this y without the bar is just at L equals 1. Okay, so this is kind of a, yes, that's it, yeah. So where 1 over L y at x and theta is equal to this y bar x over L and theta. Okay. So this is just taking away the L. Okay. So this change of coordinates appears as a small variation of the momentum. And when we do a wave packet, which is supported on a large scale L, if you transform it, kind of Fourier transform, it's going to be supported then in terms of the Fourier transform parameter, the beta Fourier transform parameter, which is theta, on a small range of order 1 over L. So it's going to modify theta by a small range. And this is what's happening. So we write psi A of x knowing theta as there's all these C, N, S, all that stuff, okay? And I'm not gonna write it. Then there's an amplitude. So A, there's stuff somewhere similar. There's an amplitude, right, which I was writing A x over L, and then there's e to the I phi x and theta. Okay? And this I write as integration in alpha of this A beta Fourier. And then I have e to the I alpha dot y bar x over L theta plus I capital phi. And now I change I change my y bar to this y, so this is beta Fourier of alpha e to the I alpha dot y x and theta divided by L plus I capital phi. So now that I have this, I recognize that this phi plus alpha over L dot y is exactly of that form, phi plus epsilon dot y, with epsilon equals alpha over L. So the L factor makes epsilon small. Okay? And so I recognize that this is nothing else but e to the I phi of the original parameter x, but at modified rapidities. And so now I get a nice expression where by using not the Fourier transform, but the Betti Fourier transform, I find that the modulated wave function on large scale, so I neglect the 1 over L squared type of term, is just the original wave function with shifted thetas. Like in the free particle case, where you do Fourier transform, you have like px, you do Fourier transform of your modulation, and then you get p plus qx. So you have a of q e to the I qx, then you have p plus qx. And here is a theta plus alpha. Right? It was important that it is a large scale so that I can just take the first order here. This is just the first order. Right? There are corrections, and one should analyze the corrections, and these are quite subtle. But without going to these subtleties, leading order, it looks like that. Once I have this, then it is simple to evolve. It is the minus I h t on psi a of x knowing theta. Then there's all these sum over n, cn, and some cn s of x, some over permutation and all this. Okay, but we are left with the n alpha e beta Fourier alpha e to the I capital phi of the sign of that, same as there, and then e to the minus I theta plus alpha over L square times t, because I know that this is an eigenfunction with eigenvalue, the rapidity square times t over 2. Okay. So, so that's nice. I get again the same form, the same dependent on x. I just have some phase, something that depends on alpha. So I have to extract now the dependence on alpha. So I have all this stuff, e beta Fourier alpha, and then I expand the exponential in time. So I have minus I theta squared t over 2, which is just a phase. Then minus I theta dot alpha t over 2L, and then higher order. And then I have e to the I capital phi of the same thing that was there before. And if I evaluate this now at, let me not repeat it, but just put the L, if I put now an LT, L here, okay, then I have an L there, and I have an L there, and these cancel out. So I just have theta dot alpha t. And this, the Bethe Fourier transform alpha times t to the minus I theta dot alpha t. If I Fourier transform back, if I look at the definition, Bethe Fourier transform is this, right? If I multiply Bethe Fourier by just e to the by just a phase is linear in alpha, it just shifts y by linear by this linearity, right? So if I multiply by e to the I alpha dot theta, it adds to y theta, or it adds to y theta t, right? And that's how y in this inverse Fourier transform becomes y plus theta t. So then if I inverse Fourier transform, inverse beta Fourier transform, I get exactly the stuff I had at the beginning. So get exactly at of x over L e to the I phi of x and theta. So I do the inverse of the step that I just did just now, and inverse Fourier transform. Then I get exactly the at that I wrote at the beginning, which is obtained by linearly evolving these y with theta t, right? So the trick is like that. The trick is that you modify your Fourier transform a little bit by combining it with this change of coordinate from the x original coordinate to the contracted one. And it turns out, that's the beauty of it, turns out that this change of coordinate is nothing else but the leading modification of the Bethe phase on the small modification of rapidities. So this change of coordinate is exactly that, right? Small modification of rapidities. And a small modification of rapidities is naturally what you obtain when you do a large scale in space, large scale modulation of your Bethe ansatz wave function. It corresponds to a small window of rapidities, so small modification of the rapidities. And that's exactly then how you get this change of coordinate that reproduces the GGG equation in the Liebniger model. Okay, so this is the trick is the Bethe Fourier transform, which combines a Fourier transform with a contraction of coordinates, and then does the job in the quantum level for these amplitude modulation, or basically these wave packets. So any question about that?
So any Bethe integrable system, this method will work, right?
Yes, it seems to be. We've just worked it out in the Liebniger, both in the attractive and repulsive phase. Here I'm describing the repulsive phase. I didn't explain that, but attractive phase, attractive values of the coupling also works. Okay, and the space of particles is different, but also works. And yeah, it's a principle because it's a general thing. You see, the Bethe wave function. The Bethe ansatz, the heart of the Bethe ansatz is this. This is the heart of the Bethe ansatz, right? This is what describes the physics of Bethe ansatz integrable model. It's a modification of the free particle phase by a sum of two body scattering shift. That's how the Bethe ansatz. And that maybe it's good to kind of and that is quite general, and although in other integral models there's a lot of bells and whistles, like here there is, right? There's a constant in front, there's S of X, the sum over permutation, all this stuff, technically they are there and they need to be taken into account, if you want to do the full computation, but the heart is this e to the I phi. And other models also have this at the heart, right? This is the basis. And then you have this similar ideas that can be applied. Now, this is not actually a formal proof, far from it. You need to analyze the correction terms, which I didn't talk about. You need to take into consideration the sum over permutation, which is a big sum, a large sum, which can modify these correction terms. You need to take into account a lot of stuff, which have not yet been properly taken into account, right? So this is still missing, right? A proper derivation of GGD equation, even 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 at like a physical level, right? It's still missing, but it gives you the intuition for why GG equation may occur and why these effective equations, dynamical equation, actually come out in quantum model. Mhm.
So
Yeah.
could there be a situation where this derivative of this phi with theta at some theta is not defined or something? There is a problem.
Yes. Yes. So now I don't know. I have to think about examples. I don't know examples, but in principle, yes, you can have situation where the scattering phase is singular. I think that I'm pretty sure I've seen quantum models where you have singular scattering phases, scattering shifts. Certainly in classical model, you do have them. For instance, in the Toda, the classical Toda model is classical, right? The scattering shifts, the logarithmic log of P1 minus P2 when the momenta are equal, this shift is very large. Of course, when the momenta are equal, the particles are unlikely to meet each other, but they do, then the shift is very large. In quantum models, now I don't have examples in my mind, but in principle, yes, it can happen. And then, in particular, this derivation is not super good, right? Some large numbers and all that. And even like the whole GG equation, the thermodynamics and all that can be affected by such singularities. You have to be careful, yeah.
And another question. So if you start from this modulated state, which is not an eigenstate, and you're evolving, and then you're saying that this state is equivalent or maybe approximated by a maximum entropy state, and that there you are maximizing the von Neumann entropy, right?
Yeah. So I
And
think this is the question of like I'm starting with this particular state, and what is that state? So indeed, so I guess in the back of my mind, the idea is I'm starting with this weird state, okay, with distribution and all that, right? With these theta, there's a lot of thetas in that state, right? Thetas are fixed, okay? These are the kind of the rapidities of my wave packets, right? The center rapidity of the wave packets, right? So I have a lot of thetas. Maybe I put a distribution of theta. So I put a distribution. So the theta n, they are distributed according to the rho of theta, say. And I put some, some distribution, say for a, right? So a of x maybe is something like maybe it's a exponential minus x minus x x0 n square over some number, something like that, and so different position, right? Product over n, something like that. Maybe I factorize it in this way. And so I start with wave packets supported at different points of some extent at some rapidities. Then I evolve that, and the kind of assumptions, or perhaps the idea, let's say, the idea is that this psi a looks like a GGE or like a maximum entropy state locally with kind of with say around around the point x x prime, take all the x zeros and all n such that x0 n is around x prime and look at the distribution of theta n, right? And that will be rho of theta x prime. So there is this idea. I mean, it's very far from proof, right? One can try to do a bit more argument, but the basic idea is like that. This rho of theta, actually, maybe I should not even write this, because this rho of theta is not the GHD rho of theta. This is the overall. In fact, I want to have something that is inhomogeneous to have non-trivial evolution. And so I say I have a distribution of xn's So the xn's are distributed. Okay. So maybe what I want to say is I have a distribution of pairs xn theta n. Yeah. And these are according to rho of theta comma x, right? Yeah, that's it. And then psi A looks locally like a GGE controlled by all these n that are, you look at the n that are near for the x and 0 is near to x prime, and then look at all the theta n's for these, and this is kind of rho of theta x prime, right? So yeah, so I guess more precisely. So I have these theta n and these x and 0, and then x and 0 theta n are distributed in some way, and that gives me rho theta x. And that should be describing the local GG that you see. Right? So that's the main idea. Yeah. So it's a bit related to the ETH. So locally, because amplitudes just vary, amplitude modulation is on large scale, locally things look homogeneous. But locally, you just see the particles such that this amplitude is supported kind of around that point. So if x0 is very large, you don't see this particle, right? And so, because this is intuition, right? And so then you see an eigenstate with a certain number of particles there, which are around that region, which looks stationary in space and time. And this eigenstate should be by ETH well described by GG for these values of theta. That's the idea. Yeah, more or less. More or less.
So if you look at two different fluid cells, and the quantum coherence between these two do not contribute to the V effective, you're saying that's what implicitly the assumption?
Yeah, totally, yeah, indeed, totally. Which is non-trivial actually, but yeah. Maybe it's not true at initial time, right? But then you evolve in time and things mix up, right? In any case, the time evolution that I described here is an approximation. I don't see all these phase effects.
So those will probably be in the next order in L.
Yes. Yes. So yeah, this is all a bit intuitive, but yeah, this is like the good question. Right? The calculation I can do is for amplitude modulation or other type of calculation, like wave packet type of calculation, but not the proper calculation of start with a local GGE. There are arguments towards that, but not fully there. Other question?
So these wave packets do not spread in time?
So it's a good question. So if you do free particle, right, in the wave packet, it actually spreads in time, right? You can check how it spreads. It's about the square root of t spreading, if I remember correctly. So they do spread in time, but at earlier scale, this spreading is small. So from the point of view of the earlier scale, then they look like point particles. That's why you can come back to point particle dynamics, essentially. But yeah, they do spread in time, yeah. But the idea is to spread smaller. Then if you go to diffusive corrections, then you might worry about that. And I think you have to worry about that. Yeah.
Hello.
Yeah.
So if we have like a 1D unidirectional Bose-Hubbard model with repulsive interaction, so that is, I think, integrable by using these algebraic Bethe ansatz. So is this kind of evolution is generalizable to non-Hermitian, non-unitary evolution like that?
Yeah, okay, very good question. So I don't know. I don't know. There will be modifications. So no, you're thinking about non-unitary evolution. So are you thinking, for instance, about Lindbladian?
Yes, like Lindblad, not Lindbladian, but algebraic Bethe integrable non-Hermitian boson Hubbard model with unidirectional.
Yes. I understand. Yeah. So okay, I'd have to think about it. But it looks just naive like that for this explicit way of doing here. unitarity is relatively important because it's important that you have these phases, like time appears as a pure phase here. And these phases combine to make the shift in Y, right? Is the phase that is, when I do the beta Fourier transform, Y appears in the phase, pure phase, and this is what makes the shift. And when you do non-retrieve ocean, it's not just phases that appears other stuff. Now, I'm sure there will be a way of doing that, but I'll have to think about it. And then also physically, unitary ocean is deeply related to kind of a Hamiltonian system, and the fact it's Hamiltonian and the fact that things move around and all that. When non-retrieve ocean is a destruction or creation of matter, right? And so we would have to take into account destruction, creation of matter. So it's not just displacement. But actually, it's a very good question. It's a very interesting problem, I would say, because I'm pretty sure there's a nice structure still that you can, because you still have integrability structure, but some bits of the time evolution will go into creation and annihilation of matter, of particles. And yes, this would be interesting to look at, actually.
And, so if there is only this few conserved quantities, not the integrable one, but we are dealing with non-unitary evolution. So whether we can think of is there any work about only hydrodynamics, not generalized hydrodynamics?
Yeah, I understand. Yeah, so I don't know of any work. It's a good question. I know people have looked at the Lindblad evolution and connection to hydrodynamics, and it's rather non-trivial. So typically, when you have creation and annihilation, you have a thing that can come and go. Then you have modification of hydrodynamics with terms that maybe destroy or create particles. So instead of having conservation laws, dt, say density of particle plus dx current equals 0, you're going to have equals lambda times something, where lambda characterizes how much particles are being created or annihilated or destroyed by the non-unitarity. Okay, so that I've seen, but full proper analysis, not really. So we have a paper where we look at Lindblad evolution, but a very specific type of Lindblad evolution that does not create or destroy matter. And then we have really hydrodynamic equation. So Lindblad evolution that satisfies some kind of detailed balance condition. There is a notion of detailed balance condition, and then it's a standard hydrodynamic equation. There are studies. I mean, we have written something about that, and there are other studies. But with actual creation and annihilation of matter, then I don't know. I don't think there's so much, but it's interesting, indeed.
Thanks.
Other questions? Okay, so this is derivation of GHD and some of its the basic ideas behind now that. Now, what I would like to do for the next thing, so there's many things one can do, structure of the GHD equation. So the GHD equation itself. So GHD equation, maybe I just say in word. Okay, so dt rho plus dx v effective rho equals 0. Itself, well, it can be extended to the inclusion of external forces. So I don't explain everything, I just write, you can write the theta effective acceleration times rho equals 0. So if you have an external force, like an external magnetic field, coupling to the number of particles, external, that couples to the number of particles in the cold atom gases, or external varying temperature or something like that, then there's some acceleration term that appears, and then you get an equation of this type where you have dx and d theta. So then you have a motion in phase space. And you have some effective acceleration like the effective velocity. This equation has Hamiltonian structure. So it's actually a Hamiltonian equation. You can write a Hamiltonian structure. You can write a Hamiltonian that gives rise to the GHD equation itself. where rho is the dynamical variable with the Poisson bracket. There's also now you can calculate Riemann invariance. So if Riemann invariance, you have Riemann invariant, and these are the things that evolve nicely under the time evolution. So the thing that are transported with the velocity. So dt n is the Riemann invariant plus vf dx n plus I effective d theta n equals 0. And this n has a simple form, is simply rho of, so n depends on theta x t, rho of theta x t divided by 1 plus integration d alpha phi theta alpha rho of alpha x t. So it turns out that you kind of diagonalize the equation where the effective velocity and acceleration gets outside of the equation. When you do this transformation, you can check explicitly. It's just a little calculation. Okay? And when the effective velocity and acceleration gets outside, that means that n is just transported on characteristics. So you look at space-time, okay? And you have so suppose I have a effective equals 0, just for illustration, okay? So as an example, okay? So there's effective velocity. So I look at some position at time equals 0, and say I take the curve, which is always parallel to the effective velocity for a given theta, right? Well, n at time t and position, that position, this is x, and at time t, at theta, that position time t is equal to n for that theta at this position x0 and time 0. This is x0. So you just, n is just transported along characteristics. The characteristics are those that are proportional to the effective velocity. And it turns out that you can use that actually to devise a solution mechanism for the GG equation when there's no external force. In other words, you can actually solve explicitly the GG equation, explicitly kind of by quadrature. So you can write explicit integral equation where x and t have been integrated. They just appear as parameters. And then you just have to solve recursively the integral equation, you get the solution to the GG equation. So you don't need to actually solve the differential equation anymore when there's no external force. Okay? And that's essentially solution by characteristic. A bit like Berger's equation, that you know how to solve by characteristic. You get some kind of various equation coupled to each other, but x and t is explicit. Same thing for the equation of generalized hydrodynamics. That's with the structure of the equation of generalized hydrodynamics, and is based on this idea of the characteristic, on this idea. So these are some of the properties of the GG equation. Yeah, questions about that?
So in the presence of the external force, is there some generalization to the method of characteristics?
Not that I know of. So of course, n, because of that equation, is transported in the 2D space x theta along the vector vf af. Is transported in that way. So that is still there, but you cannot use that to solve the equation like Berger's equation, to solve it explicitly. It's just in principle it's like that, but because this vf and af, they of course depend on n, and in a complicated fashion, it's not so immediate to solve these equations.
Right.
Yeah. It's not. I'm not sure. There is no way. It just has not been developed yet. And so, since people have looked at that like for really in quite some detail and for quite some time, then I suppose there's no way. But I don't know. Yeah. So there is still a characteristic idea, but not then giving an actual solution method. The questions.
So this external force term has been added, assuming that the external force also has the same scale of variation as rho.
Yeah, so the external force is something like that. So the evolution, instead of the Hamiltonian h, which I was writing as integration dx and some Hamiltonian density, so h of x, right? Well, it is with h evol, okay, which is going to be integration dx, and then you can put a lot of external forces. In general, you put, say, sum over I, and let me call this gamma I of x, qi of x. And this gamma I think it's related to your question, right? So that should be slowly varying. Like the initial state, you had slowly varying parameters, generalized in these temperatures. Here you have slowly varying couplings, which couple some slowly varying field, right, coupled to the conserved densities. The typical one is typical is going to be gamma 2 of x over L is just equal to 1. That's the Hamiltonian. Gamma 0 of x over L is your external magnetic field, the mu x over L. And then all the other gamma i's, different from 0 and 2, are 0. And what you get is just h evol equals the original Hamiltonian plus integration dx mu of x over L times the particle density. How I had denoted the, I guess maybe a rho or something, but particle density, Q0. And that's what you have in the actual, naturally what you have in the experiments on cold atomic gases, for instance. Right? So the external magnetic field is the term that they add. And so there's a relation between these gamma i's of x and the effective acceleration, right, of theta and x. It's a relation that one can write and relatively involve kind of a thermodynamic beta on that, and not kind of the integral equation, but one can write explicitly.
Could it be also that the when you did not have a varying external potential, let's say homogeneous potential or no potential case, where you have a set of conserved quantities, but when you put them, make it inhomogeneous potential, you need to invoke some other conserved quantities to describe extra conserved quantities or emergent conserved quantities. Is it?
I'm not sure if I fully understood the question. Yeah.
No, I'm saying let's say if we go back to the equation with A effective, at that level, without the effective term, it has some conserved quantities. With the effective terms, does it have the same set of conserved quantities or more?
Yeah, good. Sorry, thank you. Yeah. So exactly. So this is actually a crucial bit, right? H evol in general, it breaks integrability, right? Because you add an homogeneous term. In fact, as soon as you add an homogeneous term, you break. Typically, you break all conserved quantities, perhaps except a simple one, right? So some number of particles, this modified Hamiltonian, but even the momentum is broken as soon as you add homogeneity, right? Momentum is a translation variance. So in fact, you typically, as soon as you add one of them, you break all conserved quantities, even though you still write kind of conserved equations for all of them. Conservation lasts for all of them, right? But in a sense, it's not so surprising when you write the standard early equations from textbooks. Early equation like V dTV plus VdXV equals pressure. Normally, you add a force term there too, right? And the force term is from inhomogeneous fields and break momentum translation, break momentum conservation. right? Yet you write a conservation law for the local momentum, right? And well, the idea is that how do you break it? The way that you break it is in a simple way by adding a force term. Here, the force term, what it does is that it mixes the various conserved quantities with each other through this theta derivative, right? So it tells you that the conservation of n of theta for fixed theta is not true anymore, because then n of theta is related to n of theta plus delta theta, right, by this derivative. So it breaks conserved quantity, but in a simple enough way that you can write an extension of the conservation equation with the force term. Okay? But yeah, I mean, the thing is that integrability is broken. Integrability is broken. All conserved quantities typically are broken, right? Even if you say, well, I just add one potential, right, for the charge number 3 or something like that, just that one is an emoji. Still, all the conserved quantities generically are broken except for simple ones, number of particles and the homogeneous evolution Hamiltonian. And well, the question is, maybe in some cases you still have conserved quantities, and that depends on the model and all that. I don't know full answer. And the question is also, since you break conserved quantities, then eventually the model should thermalize properly, like a not detectable model, right? While that equation does not lead to thermalization, right? And what's missing is that you have additional terms beyond Euler scale, which actually do the job of thermalization and of taking into account the non-integrability. So this is yeah. So that's the situation. So conserved charges are broken, but in a weak fashion.
Okay, thank you.
Other questions? Okay, so the last 10 minutes, or maybe 12 minutes, 11 minutes. So I want to say a few words now about how we can go beyond. Now, I'm not going to be able to go, well, to fully explain how to go beyond Euler, but can we get something more out of hydro? And can we, go beyond? So this is the question, right? So how can you get more and go beyond? What does it mean get more? Well, all I described here was a local averages of local observables and how they vary in space. Time is very nice, right? There's this emergent simplified dynamics, but you may want to have a bit more. Okay? What more? Well, you cannot have too much more, because if you want some early time things now, that's not necessarily universal. So you have to look for the universal information, the large scale universal information. Right? And there is a one type of large scale universal information that is there, and these are the correlation. So this is one thing that you can get more from hydro correlation functions. And maybe I just say the basic idea here. There's a huge amount of theory, and in fact, I'm going to give lectures at ICTS. I do manage to get my visa, hopefully I do, in December, right, on this bit, the ballistic macroscopic fluctuation theory, which describe how to get these fluctuations, these correlations in integrable systems, right? And also beyond, a bit beyond, right? I describe kind of marginal theory, right? Correlation functions, how do we get correlation functions? Well, the idea is like that. The idea is that if you look in space-time, and I told you that locally the system thermalizes, right? It goes through some state now that. So you look here, this is kind of a fluid cell. And I was saying that it thermalizes maximize entropy there, but in fact, it's not quite true. So I was lying to you. Apologies about that. I was lying to you a little bit. It was still correct. Everything I said is still correct, but for a slightly different reason. Not because it actually thermalizes. Well, that doesn't quite thermalize. How does it not thermalize? Well, it's in fact what is happening. If I look at some observable, which can be a current, which can be a density, which can be anything, right? O at xt, right? If I look in the fluid cell, so the fluid cell has some length L, let's say some length L in space and some small time t in time or something like that. So I look at the fluid cell. Okay? I average over the fluid cell. The fluid cell can be at around 0 or some other position. Average over that, this observable. Okay? So this is O bar. Maybe average around X and around T. Maybe I write it like that. So 0L around X and 0T around T. Okay. Then I get some average O bar XT. So this is my O, this is my X and T, and average around it. I get some average. Okay. Now, so this is my mesoscopic scale, right? So this LT is much smaller than the variation scale, but much bigger than micro. Okay. Now, the true thing, the correct thing, is not that we have thermalization, but it's rather that this O bar in the large scale, appropriate large scale limit, apologize for the noise, I don't know what this is. In the large scale limit goes to a fixed function, I call this O bar, of fluid cell average densities. And that's what's happening is not quite thermalization to give the ensemble, but rather microcanonical ensemble. So basically, the idea is that the average conserved densities themselves, they don't move up in time, because the only way that number of particles in a cell can change is because of particles go in and out. It's just have boundary effects. Same thing for energies, the boundary interactions. So this doesn't move so much, while the generic observable changes a lot and has time to relax to a fixed function of these conserved densities. So this is the thing. And so in the end, what we have to do, we have to say that our averages of any observable, 1 point, 2 point, 3 point correlation functions in general, O bar X T, say 1 or 2, say N, they become average in a different ensemble, which is the marginal of the original distribution in space-time on specialized to the conserved densities themselves. So reduction of degrees of freedom, but at the level of conserved densities that themselves still fluctuate. So that becomes O bar 1 of all these conserved densities, say x21 and x20n. So this becomes an average in the effective fluctuating theory for the conserved density of functions of the conserved density. And these functions are themselves the equations of state. So the current is expressed as function of density and all that, right? So these O bar of Q are the equations of states. But I use the equations of state in a fluctuating fashion. Equation of state. I use equation of state in a fluctuating fashion, so that here there's a Q, okay? So that I get a fluctuation theory for conserved densities. What is this fluctuation theory? How do I describe these fluctuating conserved densities? Well, this becomes a bit more involved, okay? But it's possible in principle to describe them. And the idea is to describe the initial fluctuations using thermodynamics, and then to transport these fluctuations using Euler equation. So the Q bar, they have fluctuations at time 0 from thermodynamics, or from initial state, right? Initial state thermodynamics. And then otherwise, they are evolved deterministically with Euler equation. And this, it turns out, it gives you, if you do this procedure, you have to do it appropriately, gives you the leading large-scale asymptotics of all correlation functions. So that gives the hydro predictions for correlation function of the type some observable, it can be a current or anything else, O1, and now you look at large scale in space-time up to ON at large scale in space-time. And you look at the connected correlation function, the cumulants, the thing that I was talking about at the beginning, and it says that these cumulants, they decay like the scale to the power 1 minus n. N is the number of observable there. And there's a function in front of it, which usually denoted S, that depend on the observable O1 up to ON, and on the position x1, t1 up to xn, tn. And the hydro prediction is for this quantity. These are called the universal or Euler scale amplitude or Euler amplitude of correlation functions. So you can use hydrodynamics to get these correlation functions, to get these the way correlation functions decay at large space-time scale. And as a simple example, so this is quite general. It's actually completely general at Euler scale. It doesn't depend on integrability. It's a general theory. Okay? A simple example: if you evaluate conserved densities qi x t qj 00 in some GGE or some stationary state, integrable or not, okay? Well, that theory gives you an explicit answer for this two-point function. Of course, this is very, very simple, right? This is it's not even arbitrary observable, but you do have to write the evolution equation and all that. And what it tells you, and this has the following form. It's something we saw at the beginning with small perturbation. So delta x minus at, where a is the Euler scale, the flux Jacobian, which was a derivative of Euler current, or current in the stationary state with respect to density in stationary state. So this times the matrix C, which was the covariance matrix, and this is a product of matrices evaluated at ij. So that's a general universal formula for two-point function in stationary states. There are also universal formula for three-point functions, which are rather complicated, but which can be written in 1D, okay, that come from this kind of theory. Okay? Yeah, so I don't want to say much more about that, but I did want to show this formula, and that can be written explicitly in integrable models. So if you write in integral models, I can write, but just to give you a kind of a hint of what it looks like, it's going to be integration over all the particles. There's a rho of theta that describes the state. And then if it's the Liebniger model, there will be a 1 minus n of theta, where n is the Riemann invariant that I was talking about. And the 1 minus n is the kind of Fermatic factor. And then there's a function hi dress of theta and hj dress of theta, where hi of theta is the one particle eigenvalue of the charge qi. And the dress is just a solution to linear integral equation that involve the scattering shift theta alpha n of alpha times f dress of alpha. So this is a general prediction of two-point correlation functions. Sorry, I should put delta function x minus v effective theta t in there. So that's the prediction for the correlation functions of two conserved densities, any conserved density in energy, or density of particle or whatever, in integral models, and it has, again, a general structure. And that structure now depends on the statistics. It's fermionic, bosonic, classical. There's a statistical factor that appear there. Here, 1 minus n is the statistical factor for fermions, because in the Liebninger model, asymptotic particles are effectively fermions. But in the hadrons, you would have just one, which is factor for classical particles, etc. But then it's a general formula, otherwise general formula. And it comes out from this general theory. Okay, so this is kind of the next step. I should stop now. And from that next step, so what more can be done? Correlation functions. So get more correlation functions. Our correlation functions at earlier scale can all be evaluated explicitly with formula that get more complicated, and go beyond. This is diffusion. And diffusion, this is something I will try to explain then in my lectures in December. Diffusion is very anomalous in the integrable system. In 1D in general, it's anomalous. In integrable system, it's also very anomalous. It's not Navier-Stokes type of term. That doesn't work, fortunately. It almost worked, but doesn't. In fact, it is instead controlled by some kind of long-range correlations that appear from that theory. So the earlier scale theory of correlation functions allow you to determine the diffusive scale corrections. And yeah, so this is okay. That's kind of a going beyond. Because there's much more that one can do. And once one has that, one can ask about the phenomenology of these correlation functions, the when are there long-range correlations or not, the exact solution, the correspondence with these dynamical systems, and all these things, which are things which are still under studies. So that's more or less what I wanted to say. Yeah, so that's it for my lectures. Thank you for your attention. Are there any questions?
So this the fact that this O mesoscopic function can be replaced by this equation of state function is it's an approximation. It can be proved, or it's just an assumption.
No, it's an assumption. It's
okay. And
it's
which function? Because you said that it doesn't thermalize. So the equation of states are determined on the microcanonical ensemble that you started with initially.
Yeah, so the question of state, this is a good question. What are these functions, right? And you have to determine them. But it turns out for the earlier scale and all that, right? These functions beyond earlier scale, there are modifications you have to take into account. At earlier scale, just for this leading the functions S, which I wrote there for this one, these O bar of Q bar are exactly nothing else but trace of O exponential minus sum of beta Q. Okay. As functions, so the usual equation of state as function of the average Q's. So, and that's because this is earlier scale as the leading large L limit. So somehow this is still correct, that you just have to take, as if it was thermalizing. Except the subtlety is that not quite thermalizing, because it thermalizes to something that fluctuates. And then you want to describe that thing that fluctuates and how does it fluctuate. So this is the thing. But if you go beyond earlier scale, there's a modification to that. It's not just that function there, you have to modify it appropriately. And it's a bit of a subtle modification because it has to take into account apparent singularities of correlation functions that appear at earlier scale because of very short range correlation that are translated into delta function. So you have to take into account delta function, and then the way that it works for integrable systems or for kind of a larger family of systems is that you essentially take these functions, the same function, these equation of states, these functions there, right? And as function of the Q, you split the point. So you write Q of x plus epsilon times Q of x minus epsilon. So if a nonlinear function of Q, say Q squared, you split the point of the factor Q squared. And this point splitting regularization describes the beyond earlier correction of these kind of this thermalization. Apparently, this is what we can have arguments for that. Yeah. So there's subtlety if you want to go beyond earlier.
For all point functions.
Yes.
For all
So that's for our point function. So exactly. So you take that and that you put here for any n, and that's correct. And then if you want to go beyond Euler, there's a particular point splitting regularization that describes again all endpoint functions.
Yeah, so you're saying that for all point function, this calculation is the hydrodynamics is as if you can think of there was a thermalization.
Yeah.
But if you want to go, if you want to go beyond, then you have to take care of care of the other corrections.
So for all endpoint function, if you want to have the leading large L, that amplitude, then you can take as if they were thermalizing, but they thermalize something that fluctuate. Same thing. If you want to go beyond, if you want to have so L minus N delta S, right? That delta S, then you need to modify that.
Okay.
In fact, the power is not necessarily just power one of the change. That would be the case for integrable system, but non-integrable system is some other power that can appear and all that. Other questions?
So I'm familiar with some thermalizations in CFT, with quantum quench and so on, where I take the large time limit with the understanding that the time differences, remain fixed. And then the final function is a function of the time differences, which are small, but the the average time goes large. So, but however, what you were doing is to scale all the times.
Yes.
So it's a little different from what I do. So
yes, it is. Yes. So exactly, precisely. So if you don't scale out the time, then you get the local thermalization effectively. So then you don't see this thing that appear on long range. What I'm describing is like, if I do a little bump here, right? I put my finger on the water, then it emits some wave at some velocity, and then I can observe, right, what is there. I can observe, right? So this is a correlation function, essentially, right? It's like a linear response, if you wish, to expression of a linear response correlation function. And so what I'm describing with these things is the correlation that occur between things that are very far from each other in time and usually in space as well, although it doesn't have to be, but correlations that occur because of sound modes that propagate. So that's the thing. So things that are far in space, they decorrelate, but things that are far in time, they don't necessarily decorrelate, and they may not decorrelate if there's a mode, a hydro mode that correlates them. Nice. And this hydro mode gives a power law decay instead of exponential decay. Power law decay of correlations of exponential. Nice. And so in CFT, for instance, you would just have that at the light cone. I mean, typically you don't have other hydro velocities, and then you even looking at large time, you would have decay. Then it's sufficient to look at the finite time differences, right? But these effects are important. For instance, so these are important effects. For instance, if you want to look at something like the total integration of a current, and so this is like total current GT, and it's statistics, so like it's n cumulant or something like that, and you want to know how this behaves, then you have to know if there is a hydro mode or not, obviously zero, for instance. That would affect its behavior. Then you have to know about hydro modes for this kind of thing. There's a theory related to hydrodynamics of that. Yeah. Okay. Yeah.
Thanks.
Other questions?
Any other questions? No. So let's all thank Benjamin for a really wonderful session.
Thank you very much. Thank you for all the questions. It's really great. I think it worked quite well with the Zoom meeting, and there was a good interaction. I think it was good.
Yeah, it was.
Thanks a lot, Benjamin. It was really fantastic. I really enjoyed, and I do
Thank
hope you can come to our December meeting
Yes.
and you get your visa.
Yes. No, so I will apply in the standard route just because I tried the online thing and this was not didn't work. Yeah, so standard route. I have more time now to apply, so it's okay.
All right.
Okay.
Hi,
Thank you a
Benjamin.
lot also for all your questions. Yeah.
Hi, Benjamin. Thank you. I also enjoyed your lectures very much.
Yeah. Thank you, Anupan, also for the question and everything. Thank you for being there.
Okay,
And hopefully I will see you then in December. And I guess it's the last day of the school, is it? Yeah.
Yeah. We're closing now.
So am I the last speaker then?
Yeah.
Okay, so then I would like to thank the organizers for this amazing school. Unfortunately, I was not able to be there, but certainly this worked well for me. And well, just looking, of course, at the program, it looked really interesting. No.
Okay, so maybe I just want to thank all the speakers again for really the great lectures and putting in all the effort. And then I want to thank the program office of ICTS and the AV staff who really did a great job.